Hello all, welcome to my channel. In this video, we will discuss ways in which we can store intermediate data for Spark, and we'll see pros and cons of using each. So Spark offers multiple ways to store intermediate data, and the reason for storing intermediate data is because we want to reuse that data again and again. So that's when this intermediate concept comes. Uh, why we are calling it intermediate? Because generally Spark reads from a source and writes to a destination. So the source is a persistent part and destination also is a persistent part. For example, let's say if we are writing from a database and writing it to SDFS, both source and destination are persistent. In between whatever is there in during the job is an intermediate data that we will need for Spark jobs to work. And in that case, how do we use different techniques to write those intermediate data and read it back? So the first approach is using cache. Cache is used to store the transformations that we have done on a data frame or an object. And if we want to reuse it again, we can read it back from the cache and perform the operations again. So we don't have to calculate it twice. So that's what cache does. Uh, One thing to note is cache is a transformation, not an action. So it's what it means is if we want to have the effect of cache materialized, we'll have to make a call to an action so that that cache gets materialized. So this is what we do. Generally, df.count, df.cache.count, we can issue. The reason we do a count is that count will touch all the partitions. So there is another way as well. Like instead of doing df.cache.count, we can pass a function which touch upon certain partitions, and then only those partitions will be cached. So there are two different mechanisms. Just to know that if we do a df.cache and we call an action which only touches upon certain partitions of that particular data set, then only that part gets materialized, not the whole part. So that is one thing to note. That's why we generally do a count because count will touch all the partitions to get the count. So that materializes the whole partition, whole data frame itself. And once, let's say if we have given cache no arguments in that cache field, it will store everything in memory. And while we do have option of spilling to disk, how it will spill to disk or it will write to disk in case is or how it will evict the caches is based on the least recently used fashion. So whichever data set is or partitions is out old and not being used, that will be evicted first. It's not first in first out basis, it's least recently used basis. So that is one part of caching. Then we have persist. Persist takes an argument which says storage level, which basically says that we can persist the data in memory as well as on disk. If memory is not good enough or not free enough, then we write it to disk as well. And there are multiple levels. We will not go through that. We will see those things in a different video. But just to understand, we have an option of storing, uh, persisting the data to disk as well. And similar to cache, this also is a transformation. We have to call an action to persist the data on, and to unpersist it we can call df.unpersist, and then it will be removed. The cache will be removed from Spark's scope. Then we have checkpointing. So checkpointing is a way for us to store a particular state of a particular job. Generally, it is used with streaming, but it can be used anywhere. What it is a mechanism of storing the state and breaking the lineage. So what before we go, just a point on the lineage part. So when Spark does a lot of transformations, it stores those transformations as a DAG, and if something fails, it recomputes the DAG from a point where it things were loaded into memory. So let's say if a disk, let's say if you have a transformation X on a data frame which is being read from a disk. So let's say a file is being read from disk. So you load the file. So that becomes first transformation. Then you do something on top of it. Let's say that is X transformation. Then you add Y transformation. Then you add Z transformation. And let's say something happens. Then where does it restart from? It will restart from again reading back from the disk because the DAG is not uh, the DAG lineage is not broken. So it will always compute the whole lineage before it reads. In between, if you have cache, let's say if you have cache and that cache is materialized, so the moment you materialize the cache, then you are saying that okay, that you read it, don't recompute the DAG lineage. Same way in here, checkpoints do trigger the files the do trigger the breaking of the lineage, and that's is something which is really helpful for us to recover quickly in case something goes wrong. And generally, we provide a checkpointing location and checkpointing location, we say provide a checkpoint directory, and we can have an option of how to clean that checkpoint location so that it automatically checks out cleans that checkpoint directory. Generally, it is used in streaming case. The other and the last approach to use intermediate data is again doing an SDFS write. So let's say we read from a table in from Hive, we did some transformation, and then we are sure that okay, this thing will be used again by the downstream application. So we write it to disk, and the next stage or next part of the job reads from that particular output location and computes from there. This is a good way of doing making the pipelines reliable and less resource intensive is to break the lineage, store it intermediately, and then read it from that location. So let's say if you have something, let's say you have a job which runs for let's say very long hours, let's say 4 or 5, 6 hours it runs. So and let's say if it breaks in between, then instead of doing the again processing of the last 6 hours, if we break that pipeline it chunks of 1 hour and persist the results, whatever till now, whatever we have calculated, we write it to disk, and then we next step start from reading to that disk and then processing. So that way we are narrowing down the scope of failure or a scope of recomputation that we'll have to do, and that's a good approach that can be used. The only downside of this is the moment we uh, the moment we the moment we write to disk, it slows down the process, and it will also require a disk. So one way could be that we can always have an intermediate one location where we delete older data run and then process it from the beginning. So that can be one approach to see whether we can reduce the resources that gets consumed. Uh, so that is one. And in summary, if we see of all those intermediate storage mechanisms that we have, so strategy-wise, we have cache, persist, checkpoint, and you have to write. Lazy and eager means do we have to call an action on top of it to make it materialize? If yes, then it is lazy. If no, it is not lazy. It is an eager. Checkpointing and they have to write are eager. Storage location, cache stores in memory, persist stores in memory and local disk. Checkpointing does in local disk and remote. DF dot write can happen on local disk and remote. Uh, Deterministic. The reason we are saying deterministic and non-deterministic in a sense is, for example, uh, because these transformations are eager. So, for example, let's say you have a transformation which is adding a column to that data frame, and that data frame you are, let's say your assumption is that moment that get executed you are storing current timestamp, but because it didn't happen at that time, it is lazy, it happened when you made an actual call, so that value will change. That's why we call it as a non-deterministic one. In this case, checkpointing and DF dot write, because those are eager and that happen at the moment we call it. That's why they become deterministic. We can we can know that okay, and we can easily say that okay, what would have been the value that we wanted. In this case, being because of, let's say, or all the other say is, let's say you have something random in picture. So that random, uh, let's say if you call random two times, the values will be appearing twice, right? Two different values. But checkpointing, because we are already doing it at that time itself, so there is no way that we will see a scenario where we have a non-deterministic value. Impact on lineage, as we mentioned, cache and persist doesn't do break the lineage, and if you have any process failures, it will go back and recompute the cache as well. But in case of checkpointing and df.write, because the lineage is broken, because it is persisted to disk the moment it is called. So if something, let's say after checkpointing, you are doing something X and at that time failure happened, so it will not go and build the whole checkpointing pipeline. It will only start from the point where it has to read from the disk. Support for format. Format in a sense, do you want a specific file format to be stored these things? So cache, persist, and checkpoint does not allow you to have any specific format. A df.write will have that. So let's say this is also one interesting use case, that let's say uh, you are reading from a source which has a lot of CSV files, but you are doing, let's say, ML kind of work on that, and you have already calculated the features out of it. There is no need for you to write that back to a format which is not suited for ML. For example, in this case, uh, when you, if we use df.write, we can write it into a format which is more suitable for ML workloads. It may be Parquet, but Parquet also is not that suitable for multi-model, not multi-model, sparse values, because features generally have a lot of sparse values. So file formats like LaunchDB or Vertex, those are file formats specifically designed for ML workloads, that you can persist that, and then read downstream applications, read from that, and make use of the file formats capability. Cleanup. So cache, you have to do SQL. In SQL, you have uncache command on, and in the data frame API, you have df.unpersist that you can call. Uh, for persist, again, it is df.unpersist. And checkpointing, there is no command. You have to manually go ahead and delete that location, checkpoint location directory, and then only it will say yes, checkpoint is no longer there. And you have to write again, because there is no checkpoint, that is totally managed externally. So you write to a location, and then if you want to clean up, you will have to manually go ahead and delete that file location where you have written that. So this is the summary of the different mechanisms of storing the intermediate data and using it. Hope it was helpful. Bye bye.